Welcome to Learning with Philemon. In this video, we will be looking at how we can determine whether a molecule is polar or not. A molecule is polar when one end of the molecule has a slight negative charge and the other end has a slight positive charge. In the previous video, Intermolecular Forces, we considered the molecule hydrogen chloride, HCl. Because chlorine is more electronegative than hydrogen, the shared electrons are pulled closer to the chlorine atom. A bond in which the electrons are not shared equally is called polar. Chlorine has a slight negative charge, denoted by the delta minus, and hydrogen has a slight positive charge, denoted by the delta plus. The molecule contains a dipole, meaning that the molecule contains two poles, a negative and a positive end. The dipole can be denoted by this arrow, in which the arrow shows the negative end and the cross shows the positive end of the molecule. An example of a nonpolar molecule is hydrogen, H2. As there is no difference in electronegativity between the two hydrogen atoms, the bond is not polar. The electrons are shared equally. Note that temporary dipoles may form, as discussed in the Intermolecular Forces video. However, this temporary dipole does not make the molecule polar. Now let's take a look at some molecules with a linear molecular geometry. Carbon dioxide, CO2, has the following Lewis structure. Oxygen is a more electronegative element than carbon, so both carbon-oxygen bonds are polar. Note that the electronegativity of each element can be found in the IB data booklet. There are two dipoles in this molecule. This would initially lead us to believe that the molecule is polar. However, before we conclude this, we need to consider the molecular geometry and symmetry of the molecule. There are two electron domains around the central carbon atom. This means that carbon dioxide has a linear geometry. For more on molecular geometries, watch the VSCPR videos. The two dipoles are equal in magnitude, as both bonds are the same. Due to the linear geometry, the dipoles are in the opposite direction. As a result, the dipoles cancel out, and there is no net dipole moment. One can also consider the symmetry of a molecule. If we rotate carbon dioxide by 180 degrees around this central axis, it looks the same. Hence, carbon dioxide is symmetrical. As a result, it cannot have a positive or negative end. Carbon dioxide is a nonpolar molecule. This is a good example of how a molecule can contain polar bonds but be nonpolar. Hydrogen cyanide, HCN, has the following Lewis structure. As carbon is more electronegative than hydrogen, and nitrogen is more electronegative than carbon, two dipoles are created. Note that the dipoles are not necessarily of equal magnitude. This will depend on the differences in electronegativity. Hydrogen cyanide also has a linear molecular geometry. However, unlike in carbon dioxide, both dipoles are in the same direction. Therefore, they do not cancel out. There is a net dipole moment, depicted by this larger green dipole. The end of the molecule with nitrogen has a slight negative charge, whereas the end with the hydrogen has a slight positive charge. Note that the molecule is unsymmetrical, as the two ends of the molecule are not equivalent. Now let's consider some molecules with a tetrahedral molecular geometry. Methane, CH4, has the following Lewis structure. Carbon is a more electronegative element than hydrogen, so all four carbon-hydrogen bonds are polar. There are four dipoles in the molecule. There are four electron domains around the central carbon atom. This means that methane has a tetrahedral molecular geometry. Methane is also a symmetrical molecule. If you rotate methane along this axis that lies along the carbon-hydrogen bond, it will look the same. This works no matter which carbon-hydrogen bond the axis is placed along. As the tetrahedral shape is three-dimensional, I recommend you use the MolView website in the description or a Molymod to visualize the symmetry. As methane is symmetrical, the dipoles cancel out. There is no negative and positive end in the molecule. One can think of the positive charge surrounding the molecule due to the less electronegative hydrogen atoms, and the negative charge being in the center due to the more electronegative carbon atom. Fluoromethane, CH3F, has the following Lewis structure. Carbon is more electronegative than hydrogen, and fluorine is more electronegative than carbon, so there are 4 polar bonds. CH3F also has a tetrahedral molecular geometry. However, it is not a symmetrical molecule. If you rotate fluoromethane along this axis, it will not look the same due to the presence of the fluorine atom. As a result, the dipoles do not cancel out. The end of the molecule with a fluorine atom has a slight negative charge, as denoted by the net dipole moment. Yet again, we see molecules with the same geometry, but one which is nonpolar and one which is polar. Now let's look at another example. Ammonia, NH3, has the following Lewis structure. Nitrogen is a more electronegative element than hydrogen, so ammonia contains 3 polar bonds. There are 4 electron domains around the central atom, like in methane and fluoromethane. However, in this case, there are 3 bonding pairs and 1 lone pair around nitrogen. Therefore, the molecular geometry is trigonal pyramidal. Due to the presence of this lone pair of electrons, the molecule is asymmetrical. The bottom end of the molecule has hydrogen atoms, whereas the top end has this lone pair of electrons. In some diagrams, you will also see a dipole drawn for the lone pair of electrons, as there is a higher electron density of electrons in the orbital than near the nitrogen nucleus. Ammonia is a polar molecule, with the top of the molecule having a slight negative charge and the end with the hydrogens having a slight positive charge. As you may have noticed in the previous slides, there is a clear pattern that helps us distinguish between polar and nonpolar molecules. Nonpolar molecules may contain nonpolar bonds. Some nonpolar molecules contain polar bonds but are symmetrical. Nonpolar molecules experience only London forces. Polar molecules contain polar bonds and are asymmetrical. Look out for the presence of lone pairs of electrons around the central atom, which will most likely lead to asymmetry. Polar molecules experience London forces, but also dipole-dipole interactions. They may also form hydrogen bonds. For more on this, watch the previous video. Thank you for listening. To consolidate your learning, try to identify which molecules in the description are polar. If you haven't already, please subscribe for more content. Stay curious.